Jai Hind everyone. Myself, Dr. Suvarna Mujumdar, Assistant Professor in Electronics and Communication Department of Akgec Engineering College, welcomes you on a lecture on digital to analog converter. First of all, we will discuss what is this digital to analog converter and what is the importance, why we are going to learn this digital to analog converter. So, before going to the discussion on what is digital to analog converter, I just wish to share that all the information or whatever say the content or data, or I can say the quantity that which we are going to measure in this world, all are in analog in nature, or I can say physical quantities which will like temperature, humidity, any quantity, all are in analog in nature, or I can say they are continuous in nature. So when we say the continuous data is there, we have to capture this data and then we have to process that data, or we have to amplify signal, or we have to take or extract the information from that physical data. So first of all, we have to convert that physical data into an electrical signal. For that we need sensors and transducer, and after that we get that electrical signal and we wish to process that signal. When processor is there, when processor come into picture, that processor is a digital system. Digital system is they work on binary data. So every processor, whether it is DSP or microprocessor, they work on digital data. So we need a converter which convert analog information into a digital. So we have one more device that is known as A to D converter, analog to digital converter, which will be coming into first after sensor get the data, we have to convert that into a digital form. So A to D converter is there. Then we process that data through any microprocessor, and after processing we have to again send that data back to the information. Like for example, the voice is first converted into an electrical signal, then converted into a digital signal. When then we process it, and at the receiver end, that digital data has to be again converted into an analog form, and at that place this digital to analog converter come into a picture. This digital to analog converter basically converts our analog information into a digital information into a analog form. So for example, we have 1010. So this DAC will convert this as an analog signal, and for this conversion they need a circuit, and this converter circuit converts this DAC with some reference voltage, so that we will get this peak value. Okay, depending on the weightage available, this data get converted into an analog form. Usually there are two types of D2A converter which is in the market. The most popular one was the R2R ladder, but we will discuss both the one, binary weighted, or we can call this at a weighted register DAC. Both these type of DAC consist of switches for digital data 01, registers, and op-amp. Op-amp is nothing but an operational amplifier which is used to amplify the signal and make it available for to drive the another circuitry. So first of all, we will discuss about binary weighted register DAC. So in case of binary weighted, it utilizes the summing property of DAC. So here in this case, you will see that we use op-amp in an inverting mode. There are two modes in which we will use op-amp. One is non-inverting, and here we are using inverting mode. Inverting means for with the negative terminal we connect our overall circuitry. So here the gain will be minus RF by R1. RF is this feedback resistor, and R1 will be the equivalent resistor which will be generated from here. Okay, So in binary weighted, for each binary bit, for example, if we are designing 4-bit DAC register, in that case, we need 4 different type of registers, one with R value, one with 2R value, then 4R, and then 8R. So all the registers are in the power of 2. 2 to the power 0, 2 to the power 1. So we called it, that's why this DAC is known as weighted register DAC. Here the register is assigned with some weight. Here you can see that MSB is connected with the register R. So its weight will be 2 raised to power 0, that is 1. then next bit will be connected to 2R and the LSB will be connected 2 raised to power n, where n will signify the bit of the DAC. For example, 4-bit DAC, 8-bit DAC or 12-bit DAC. So in that case, if it is 4-bit DAC, 2 raised to power 4 minus 1, that is 3. So its value will be 8. So 8R will be the weight given to the LSB position. Then we have the switches. Now here this switch will be either connected to 1 or 0, or I can say will be connected to VCC or ground. So depending on the input connected, the digital bit connected, that particular position will be having value, the current will flow. Like in MSB, the current we represent it as IN minus 1. So if MSB is 1, then this current will be available. If LSB is there, then this current will be available. So accordingly, the value will be there. So here we can say that this is a current device, or we can say here we consider current as a source for traveling, and this current, as X is having an infinite here, infinite resistance, so this current will flow through this RF and it will be available here for output. So we will have a signal at the output side. So in this way, this digital data is converted into an electrical signal, or we can say an analog signal through this device circuit. So this is an example where we consider that if it is connected, for example, the MSB is connected to 1, we can take this as a 4-bit DAC. So here 4-bit DAC means 1R. So this say 2R, 4R, and this will be 8R. And let us take an example. So suppose our data bit is 1010. So in this case, MSB, that is this switch, will be connected to 1. This second switch will be connected to 0. The third switch will be connected to 1, and this fourth switch will be connected to 0. So in this case, this II output current will be IN minus 1 plus I, or I can say IN minus 1 instead of IN minus 1, it is I3 plus I1. Okay. No, this will be 2. Okay. So two currents I3 and I1. As we use the value of R will be 1 kilo ohm, or it depends on the value, what voltage we required at the output at, we decided the resistance value, and accordingly the current will flow. And if we are using 5 volt as a reference, that for 1 we use 5 volt, and for 0 if we use 0 volt, then in that case this V1 will be connected, means switch is connected to 5 volt. So 5 volt value, the current will flow through 5 volt. So in this way we will generate the current, and at the output V0 we will have minus RF into II. So the advantage of using this weighted resistor is that the construction is simple and it is a fast conversion. But there is a disadvantage, and that's why we are not using this in a practical cases. The requirement of the resistance, a large range of resistance is required. For example, if we have a 12-bit DAC, then in that case we have a combination, we need 2 raised to power 12 and variety of resistance with high precision. And this lower resistance with this high precision, it is very difficult to obtain, and it requires a low switch resistance in the transistor also. And this circuitry is very expensive, as we have a variety of resistance are required and we have to match them resistance. And so usually this weighted resistor DAC is limited to 8-bit resolution only. Now, what do you mean by this resolution? So we can define the resolution is the smallest change that can occur at the input side, or at or we can say when we change the digital data from 001 to 0010, this change is occur at the input side. So by doing this change in a 1 bit at the input side, what will be the change in the output? So in case of resolution, it will be defined as, we can call it as R, and it will be having, if we calculate this in a percentage, it is step size divided by full scale into 100. Okay, or another is 1 upon 2 raised to power n minus 1 into 100. What does this mean? That when we change an input bit by 1 value, what will be the change occur at the output side? What will be the voltage change in the output side? For example, if we calculate here for 2 raised to power 2, n equals to 2, in this case the resolution will be 1 by 4 minus 1 into 100, 100 by 3. Okay, so as the number of bits increases, we get the proper resolution, we get the nearest value. Now the second type of D2A converter is R to R. As weighted resistor has a disadvantage that we need different type of resistance, range of resistance are required. So to recover this disadvantage, R to R ladder is designed, and this is the most popular DAC which is used in the industry, or we can say in the practical case. In this case, we need only two types of resistance. One is R and one is 2R. So if R is 1 kilo ohm, then we require 2 kilo ohm. The combination of these two resistance is sufficient, and RF will be also having the value which is equivalent to 2R. So in this we can have R to R combination only, and again we need switches and we need an op-amp. Here also we connect the op-amp with the inverting mode only, but so that we can get a negative, but yeah, current will flow, so it will get rectified it. So here the reference VR may be 5 volt, maybe 3.3 volt. It depends on the DAC design and circuitry. So this VR, if it is 5 volt and switch is connected to 1, then this 5 volt battery will flow the current in this case. And the overall, if we solve this circuitry and we find the resistance value, then the overall resistance will be 2R. Whenever we find this, or if Thevenin's, we will use Thevenin's theorem to resolve this, to solve this circuitry, and we will find the values for this. So this is the generalized diagram where we have MSB is connected near to the op-amp, or this will be having 2R, and LSB is connected far away with this resistance. So let us take an example of 3-bit DAC. In this 3-bit DAC, we will take a combination 001, that LSB is having one value and other two MSB, and the next bit is having connected to ground. So you can see that with the diagram, MSB is connected to ground, the next bit is also connected to ground, and LSB is connected to the reference voltage. Here we are taking VR, you can take the value as 5 volt also to solve the problem. Now we have to find the equivalent resistance so that we can connect it, and an equivalent voltage so that we can resolve this circuit. So for that we will find the values. So you can see from the diagram that we have removed this op-amp, and now we are observing the voltage from one point. One is Z point, one is Y point, one is X point. Okay. So when you are pointing from X and you remove this resistance, these two resistance, 2R and next resistance, here when we have one resistance also 2R. So these two resistance are in parallel, and when resistance are in parallel, the resistance equivalent resistance will be R1 into R2 upon R1 plus R2. So if both the resistance are same, then the equivalent resistance will be R. So this terminal, at X terminal we have value R, we connect it as R, and we will connect the battery or this VR as VR by 2, because the resistance is parallel and the voltage is divided, and we will have the resistance voltage value as VR by 2. Now we connect this in series with this second R and 2R. Now at point Y, now we have to find the resistance value at Y terminal. So at Y terminal, we find again, we remove this battery source and we find that again this is 2R, R into R plus R, because these two R are in series. So these two R are in series and we get 2R, and this 2R is get in parallel with R. So equivalent resistance will be R. And again the battery, or we can say it is divided into two blocks. So VR by 2 is the battery. Now VR by 2 is again divided into 2. So we are having VR by 4 or 2 raised to power 2. So now the battery which is connected is VR by 4. Now when we see at terminal Z, at terminal Z, this R and R will again become 2R, and this we remove the potential and we will find the equivalent resistance, and here again this will be R, and now our battery is VR by 4. So it is again divided by 2, so it will become VR by 2, 2 raised to power 3. And now this will be connected to this Z terminal here. So at op-amp side, we will find that the total resistance, or we can say it is connected as 3R, and the potential is VR 2 raised to power 3. Okay, or we will have this equation, a generalized case equation, and here we will substitute this as we solve this. So for any case, if any battery, suppose in this case we have considered battery is connected to LSB, that is LSB is having 1, other both cases are 0. If case is 0, 1, 0, then in that case also we will get this value only. So we will consider this as a generalized case, and here we observe that for LS the equivalent resistance will be 3R, 3R and 3R. Now battery is connected. So for MSB it is half VR by 2. For next bit it is VR by 4, and for the LSB it is VR by 2 raised to power 3. So generalized, if it is a 4-bit DAC or 5-bit, so 2 raised to power 4, 2 raised to power 5, like this we can connect the batteries. And in that case this will be 4R, 4R, 4R. Now we will find the generalized equation for this, and here it will be RF by 3R. The negative sign is for inverting terminal, and the overall potential, or we can say the gain for this op-amp, if one source is there, the gain will be minus RF by 3R. So here the gain will be minus RF by 3R, and the potential is VR by 2 raised to power 3, and B naught represent the switch. B naught is 0 or B naught will be 1, the switch which is connected. If it is 0, then the overall term will get cancelled out and it becomes 0. Here we multiply this both the term with 0. So if we take the common value RF by 3R, and we are now VR by 2 raised to power 3, these are the common terms which we can take out, and when we take the LCM, or I can say, it will become 4B2, 2B1 and B0. Now here if I place 0, 0, 1 like this, so these are 0, so this will be the result which we obtained in last slides. So this way we will calculate the potential for a particular digital data, and as I told that we are converting digital into analog signal, so you can see that this is the way we get the result. For each digital data, we have some potential, and these potential, when we connect, we will get a linear range, and this will be the conversion of an analog digital signal into an analog form. So the advantage of R2R DAC is it is only 2 resistors is required. One is R, another one is 2R, and we did not require any high precision. Like in weighted one, we require high precision because we have a range of that and we wish to have connected with them. The disadvantage is this: speed is slow. So as compared to binary weighted, but again the advantage is more prone to this, so we use R2 or DAC in the current situation. Thank you.